And welcome back, Mindsetters. Welcome to the session, Mindsetters.
They went with us.
Yes, it's been a long day. But anyway, Mindsetters, I hope you guys are ready for this session of Learn Extra Live. Make sure that you have your pens and pads out and you're ready to make notes. Grade 12s. Yes. I'm your boy Ty, and I'm handling. I'm here with Tracy. I'm handling this session with Tracy.
No, and he is handling. It's been a lot. We've done 2 sessions together already. It's been a long day, especially for you. I'm sorry. Okay. Anyway, grade 12s. We're going to be looking at the electromagnetic spectrum today. We're going to look at what it's made up of, what we use it for, and then we're going to add some extra equations into it using what you learned from photoelectric effect last week with Bruce. Okay, and I have learned some things from Phil, because I know you're missing him by now, but I have a challenge question for them, but we'll get to that in a second. But it's actually a nice section. It's a nice, easy section, but lots to learn.
All right. So on that note, while you head across to the board, I'm going to tell these Mindsetters, make sure you get on the page, get chatting to me, let me know what you guys are thinking. If you're lost in here, if you need help, post, because so you know, I have these awesome prizes that I need to get rid of. So make sure that you guys get on the page and get chatting to us. Let me know what you're thinking, because the best post will get these awesome prizes sent to them, this Casio calculator and this awesome labeler. And I want to say, Mindsetters, make sure you tell a friend, tell another friend, because yes, we're trying to push up those numbers. Right now, we're at 14,500 couple of people. So we're trying to get to 15,000 now. But we can only do that with your help. So, on that note, this is where I hand over to Tracy. Tracy, take it away.
Oh, thank you, Ty. Okay, so before we jump right in, here is your challenge question. Okay, you don't need to rush too much about taking it down. I'm interested to see how many of you get this right. We will be posting the challenge question onto the website, onto the Facebook page in the next break. Okay, so question is, the energy of a photon associated with a beam of monochromatic electromagnetic radiation is E. Okay? Energy of a photon. Oh, that's black. You can't see black on black. Anyway, if the wavelength of the radiation is doubled, the energy of the photon is now. Your option A is the energy divided by 4. Option B, the energy divided by 2. Option C is twice the original energy, or option D is 4 times the original energy. In other words, I'm asking you, if we have a wave and I double its wavelength, what happens to its energy in relation to its original energy? We are going to look at that, but it is also related to what you did last week with the photoelectric effect. Okay, so let's jump right into the electromagnetic spectrum. Okay, and once again, the board doesn't actually like me. What makes the electromagnetic spectrum so special? Number one, it has a huge spectrum. Okay, we've classified it into 7 main parts. Okay, those are where we can see the base differences between them, but it's huge. Okay, it ranges over a whole bunch. It is what the electromagnetic spectrum creates, what we call a natural speed limit. Okay, which is 3 times 10 to the 8. Guys, there was some stuff in the news recently about the possibility that things can actually travel faster than the speed of light. We're not sure about that, okay? This is something scientists are going to be working on for a good few years still. And the honest truth is, even though and once again, it's sci-fi, where we talk about being able to travel faster than the speed of light, or we go at 3 times the speed of light, 4 times the speed of light, 100 times the speed of light, especially in things like Star Trek and all those sort of things. The honest truth is, we're not sure what would happen to matter, okay, at those sort of speeds, whether we would still be matter or whether we actually change into energy. So it's this whole debate still, but we're still considering, for all intents and purposes, nothing can travel faster than the electromagnetic spectrum in a vacuum, which is 3 times 10 to the 8. Electromagnetic spectrum, what you did last week, photoelectric effect, has a wave nature and a particle nature. Okay? Some parts of the spectrum has a greater or more prominent wave nature, okay, like radio waves. Some parts of the spectrum has a more prominent particle nature, like gamma rays, okay, which means they behave more like particles, but they have both. And remember, we know they have a wave nature because they can be reflected, they can be refracted, they can be diffracted, okay, they have those wave properties, but at the same time, they behave like a particle, like we saw in the photoelectric effect, which you did with Bruce last week. And so we know that they can also behave like a particle because they can kick electrons out of metals, okay? And then, very, very important, no medium is required. They can travel through space. Makes them very, very special, okay? Now, how are electromagnetic waves created? Now, this is when I start to look like a little bit of a what's the plasticine man? Okay, electromagnetic spectrum. In the sun, let's start with them. In the sun, we have a huge nuclear explosion happening, okay? Constantly happening. Because of that nuclear explosion, we have tiny little charged particles constantly moving within this nuclear explosion. Those charged particles are like alpha particles, helium nuclei, hydrogen nuclei, all of these sort of things. It's tiny little particles are moving. You learnt in grade 11 that when a charged particle moves, it creates a magnetic field. So these charged particles are vibrating, okay, and the electrons inside are vibrating. They vibrate up and down. As they're vibrating up and down, they create an electromagnetic a magnetic field. And that magnetic field follows the charged object. So it goes up, and then it goes down, then it goes up, and then it goes down. So it's creating this magnetic field. But you also learned last year, and you should have done a little bit of this in electrodynamics, that when we have a change in magnetic field, that change in magnetic field in turn creates an electric field, but they're always at right angles to each other. So what's happening is, and I'm going to try to do it this way so you might sort of at an angle type thing. So you have the magnetic field doing this, going up and down, up and down. At the same time, you have and I really am, it's like trying to rub you. Yeah, okay, yeah, but it's not, stop it. Okay, so magnetic field goes up and down.
While you explain, I'll do it.
yeah, anyway. And the electric field goes sideways, okay? So you've got this happening. There you go. Okay, you got this. One going up, one's vertical, one's horizontal. But they happen at the same time. So as the magnetic field reaches its crest, electric field reaches its crest. And I've opened the calculator in the process, okay? Didn't even touch the screen. I love this TV. As it reaches rest, they both reach rest. As it reaches trough, and I can't go further in it because my arms are too short, they reach their troughs, okay? So the point is, they create each other. So the creation is a charged particle which creates a magnetic field, which in turn creates a perpendicular electric field. So you have an electromagnetic wave created by an electric field and a magnetic field. Okay, charged particles. Then, the wave equation. In fact, we've just done that. Ty's starting to feel like, I've heard this before today.
Yeah, this is all very familiar.
Sounds vaguely familiar. You know, trust me, it sounds only vaguely familiar to them too. Okay, wave equation, V equals F lambda. You did this in science. Still valid for a wave, except now we're going to use a special version of V, and maybe I should have a pen. Instead of V, we're going to use C, because we're going to use C, and C is specifically the speed of electromagnetic radiation. You've learned it as the speed of light. Light is only one part of the electromagnetic spectrum, so that is 3 times 10 to the 8. Of course, it will be given to you, but I really hope you guys know that by now. Okay, now, let me see if I can actually make this a little bit bigger for you, because this is ridiculously small. Okay, let's just... oh no, that doesn't. Okay, so here we go. And I'm covering up our logo. I'm sorry, but it's okay. Here we have our spectrum. Guys, it really is worth trying to download one. There's probably one in your books. You have to know this, by the way, okay? You don't have to know the spectrum in detail as in knowing, I don't want it to go anywhere, in knowing, for example, that radio waves have wavelengths of between 10 to the 3 to 10 to the minus 10 meters. You don't need to know that, but you do need to know that radio waves have the longest wave, shortest frequency, and gamma rays, shortest wave, highest frequency. Okay? Now, what I like about this particular, and I've done it again. Oh, good, it's fine. Is we're going to look at from radio waves. Okay? Guys, please be careful, and I've seen this. couple of years ago, my matrix got completely bent out of shape because in a Doppler effect question, they got asked about radar speed guns, which they were fine about until they said, well, it works on the principle of using radio waves. And as soon as you hear the word radio, you go, ooh, sound. No. Radio waves, not radios, radio waves are electromagnetic. Okay, we associate it with sound because radio waves give us radio. Biggest use of radio waves, radio stations, okay? They have very big, up to 10 to the 3, which means their wavelengths can be as large as a kilometer, okay? Kilometer long wavelength, brilliant. Which also means, though, that their frequencies are quite small, 10 to the 6 to 10 to the 10. So that's 10 megahertz to just over to about 100 gigahertz, okay? They, in terms of, the nice thing about this picture, in terms of their size, they relate it to about the size of people, okay? Unless it's a really small person with 10 to the minus 1, that would be 1 meter, and that I'm even taller than 1 meter, so, you know, it's about
Barely.
that. Yeah.
I'm joking.
No, only barely. I agree. It's about that. Yeah, don't go there. Okay, moving on. She's national television. Okay, and all my special children are watching right now.
And they're rolling on the floor.
Pretty much taking photographs and going, "That's my teacher, Mom." Anyway, then we get to microwaves. We all know what microwaves are used for. Which is used for what? Ty, you're a single man.
Yes, it's for heating up food.
Food,
and
yes,
leftovers.
because we don't use the stove.
I have seen
Sometimes.
it. It's in the kitchen. I don't know what it's for.
Okay, brilliant. That's what bachelors do. Okay, don't worry, bachelorettes do exactly the same. It's a lie that we all cook. Okay, anyway, your microwaves are slightly longer, higher frequencies. Their wavelengths are in the range of the size of an ant. Okay, so you can still sort of see them, but they're starting to get smaller. In the bridge where we start to now get infrared, we're talking about wavelengths that are about the size of the eye of a needle. Infrared, very good. We use infrared technology for time.
Passing information through phones at some point.
We
That
can
is-
use infrared, same with Bluetooth, but also, you know, in the movies, the army and them use it to look for hotspots.
Yes.
Okay, so we can use it to find hotspots. Infrared on satellites, they can find the
Remote.
hotter something is, the redder it glows. We actually give off infrared radiation, which is why they can actually see it.
Yes, our heat.
It's our heat, so
signatures.
actually we all are hot. We're not actually cool. Cool doesn't really work.
Technically.
So we all actually are hot. Moving on. Okay, like we said, I shouldn't give up my day job and become a comedian. Okay, then we get into infrared, sort of squeezes into visible light. And visible light, my producer's laughing in my ear. How rude is that? Visible light is infrared, is red, orange, yellow, green, blue, indigo, violet. You do need to know the colors of the rainbow. These are the ones you do need to know what their wavelength ranges from. So it's 700 nanometers to 350 nanometers, okay? That one you do need to know. Make sure you understand that. Also, with the visible light, I'm sure you've seen this when you did diffraction, you need to know which ones are longest, which ones are shortest, because that affects the degree of diffraction. So you spent a lot of time on visible light along the way. Now we start getting into our really small wavelengths where, for example, as we go into ultraviolet light, the wavelength is about the size of a virus, which just makes it sound very scary. Okay.
Yeah.
As ultraviolet light, as the wavelength gets smaller and smaller, it now starts to be comparable to the size of a protein molecule. Gets smaller and smaller as we get onto X-rays. X-rays wavelengths are around about the size of an atom, whereas gamma rays are the size of nuclear. Their wavelengths are the size of nuclear, of atomic nuclei. Okay. Once we get to the very small wavelengths, okay, they become very high frequencies. High frequencies mean they have lots and lots of energy. The more energy they have, the more like a particle they are going to behave, which is why gamma rays are so dangerous. They don't have a lot of uses for us. X-rays become useful for us because they start to behave like a particle. And I'm hoping you all go, I know what X-rays are useful for. To take X-rays. Surprise that. To take images of the bone.
Surprise.
Because X-rays can't pass through the density of the bone. They can pass through the soft tissue, but the particles then get stopped by the bone, which is then where you see the reflection. Ultraviolet light, probably the main uses for ultraviolet light, sun tanning. Okay, not the best thing to do with it, but you can. Ultraviolet
Forensic
light.
Sciences.
Sorry.
Forensic Sciences.
Forensic
like
sci-
when those
yes,
guys go into
yes,
CSI.
CSI, when they put the luminol, there we go, and they put the stuff on, and they make it all glow in the dark. It's a little, it's a little,
Some of it is a little far fetched.
no, it's a little added to it, but it is the whole concept. Black light in on stage, okay, black
Exactly.
lighting. Ultraviolet is the nice stuff that because it allows things to what we call photoluminous, which not that I said that right, which allows things to glow because it's a chemical reaction
the
that
dark.
happens. Glows in that light, yeah. Well, even ultraviolet light, if we had to have, say, ultraviolet light in the studio, ooh, heaven forbid, okay, even on here you would see my white part of my shirt glow, even without it being completely dark. Though in dark it just looks more exciting, you know. And then
Exactly.
you just see all sorts of things that you don't really want to see, and we move on. Okay, infrared, visible. Just if they ask what is the main use of visible light, please just don't be silly about it. It's so you can see things. Okay.
Simple.
It's very obvious. Just be careful with that one, okay? And I think we've done with that one for now. Lots of information. I think it's a good place to take a break.
I think so
And
too.
then we're going to move on with some more stuff.
All right. So on that note, if you guys are just having as much fun as we are, make sure you get on the page, get chatting to us, let us know what's on your mind. But on that note, do not disappear. We'll be right back after this break.
Yes.